Hey guys, it's Mr. Sheelan here. This is going to be the video covering all the check your understandings for the Unit 5.2 notes covering Newton's laws of motion. Okay, so again, not going through the notes, just simply going over the check your understandings. So check your understanding number one here. So after you've gone through what Newton's first law of motion is, in the absence of an external force, a moving object will do what? What's a moving object will do? So thinking about if we toss a baseball out in space, what will happen to that baseball? Will it stop immediately, slow down, and come to a stop? Will it pick up speed? Will it continue? Will it accelerate? Will it move with a constant velocity, or do we need more help here? So what we should have realized is that, well, if we're out in space and in the absence of an external force, so nothing is affecting this ball, we toss a baseball and that baseball moves at 5 meters per second, that baseball is going to move at 5 meters per second literally forever until something comes along and hits it. So our answer here would be D. It's going to move with a constant velocity for nearly forever. Okay, so now let's think about number two. So we're still out in space. When a rocket engines on a spacecraft are suddenly turned off while traveling in empty space, what will the spacecraft do? Will it stop immediately, slow down, eventually stop? Will it increase speed, or will it move at a constant velocity? Now, a lot of us, I'm sure, want to say B. It'll slow down, and eventually it'll come to a stop. We want to think that because, well, that's what would happen with a plane. Like, let's say a plane turns off its engines. Well, the engines were allowing it to continue moving forward, right? And if they turn off the engines, the airplane will basically just fall out of the sky. It won't move as quickly forward as it was before. But we're out in space. So it's not going to slow down because there's nothing affecting the spaceship out in space. There's no external forces, so it's not going to stop immediately. It's not going to slow down. It's definitely not going to pick up speed because you need an external force to do that. You would need something to come up behind and push it. So the answer here is also going to be D. It's just going to move at whatever rate it was last moving at. At the moment that the rockets turn off, it's just going to keep moving at that rate. It's going to flow down forever. And then number three, you're standing on a moving bus facing forward, and you suddenly fall forward. You can infer from this that the bus is, what, changed? Did its direction change, but its velocity or its speed stay the same? Did its velocity increase or its velocity decrease? Well, just like our car idea, if we're standing on a bus here, bus is moving this way, we'll say at 30 miles an hour, right? 30 miles an hour. And then all of a sudden, let's say that the bus puts on the brakes, and then all of a sudden, boom, that bus is now going, say, 20 miles an hour. Okay? What speed are you going to go at the moment that it goes from 30 to 20? You are still going to be moving at that 30 miles an hour. Because you're on the bus, yes, you're a separate entity from the bus, but you are still on the bus traveling at what the original speed was. You're going to continue moving at 30 miles an hour. The bus is now moving at 20, and you're going to fall flat on your face on the bus. So the answer here is A. The velocity of the bus decreased. Okay? And so this would be just Newton's first law. The bus changes its inertia. It went from 30 to 20 miles an hour. However, you are not part of the bus. The brakes are not, attached to you. You are not attached to the frame of the bus. So you're going to continue to move at 30 miles an hour and fall flat on your face. Okay? All right. So that is it for those check your understandings. So now let's just quickly go through these check your understandings. So the math portion of Newton's laws of motion. So a 3.5 kilogram, oh my goodness, 3.5 kilogram object experiences an acceleration of 0.5 meters per second squared. What net force does the object experience? So this is what we're working with here. We have the mass, we have the acceleration, we need to find the force. So that means we're going to be using this equation here. Force is equal to mass times acceleration. So we'll plug those in. So for m, it's 3.5. For a, it's 0.5. And what we would end up here, 3.5 times 0.5, that would give us 1.75 newtons for our answer. 1.75 newtons for our answer, okay? Check your understanding. Number 5 is pretty much the same thing. We're looking for a force. What is the force required to accelerate a 1,000 kilogram object? So we're working with something that's super huge. And it's a sports car that's accelerating here at 6 meters per second squared. And we need to find out what the amount of force is needed to move it at this rate due to its mass here. So again, we're going to use F is equal to m times A. So it'll be m, or 1,000, times A, which is 6. And what we should have gotten is that F is equal to 6,000 newtons. Okay. Easy peasy, just finding force. Number 6, a 12 Newton net force acts on a 36 kilogram object. How much does it accelerate while the force is being applied? So we've got F is equal to 12N, 12 newtons. And the mass of this object is 36 kilograms, and we want to know, well, what was its acceleration? So in order to find acceleration, that's going to be F divided by m. And then we just plug in our values. So it'll be 12 divided by 36, which is going to give us here roughly an acceleration of 0.33 repeating meters per second squared for our answer, 12 divided by 36. The number 7, a bat strikes a 0.145 kilogram baseball with a force of 5,800 newtons. What's the acceleration of the baseball that it experiences? So we've got mass of the baseball, 0.145 kilograms. We've got the force used, 5,800 newtons. And we're trying to figure out what the acceleration of this ball was. Well, again, we're going to use acceleration is equal to F divided by m. Acceleration here is going to be 5,800 divided by 0.145. And what we should get for acceleration is 40,000 meters per second squared. That's an insane speed. Okay, so for every second that passes, the velocity of this ball is going to increase by 40,000 meters per second. Okay, like that's insane. And then number 8, an electric model train is accelerated at a rate of 8 meters per second squared. And in order to accelerate that quickly, there was a 12 Newton force applied to it. What's the mass of this electric train? So we're going to use the equation m is equal to F divided by A. Plug in our numbers here, so it'll be 12 divided by 8. And then we should get here for our mass, I think it should be like 1.5, isn't it? Yeah, it's 1.5. We should get here, mass is equal to 1.5 kilograms. Okay. And then lastly, looking at these last two, check your understandings. You're sitting in a chair, and you feel the chair pushing up on you. The reaction force in the situation is which of these options? Is it the chair pushing down on the ground? Is it air pushing down on you? Is it you pushing down on the chair? Is it the ground pushing up on the chair? What is that? What is the opposite force from the chair pushing up on you? Okay, well remember Newton's third law of motion states that for every reaction there's an equal and opposite reaction, equal in magnitude but opposite in direction reaction to that force. So if you're sitting in a chair, okay, You're sitting in a chair. You're so happy. You've gotten to sit down. Yay, we're sitting down in a chair. If you're sitting down in that chair, okay, and the chair is pushing back up on you, that means that there has to be something pushing back down on the chair. Which one is it? Well, it's not this one. Well, it's not the ground pushing up on the chair. It's not the ground pushing up on the chair. Okay, that's something completely different. Is it the air pushing you down? Well, the air really doesn't push you down. Okay, gravity pulls you down, but that's not the same thing. So really what we're left with here is that, and this is where you've got to think about it for a second here, that this works in a pair, right? The chair is going to push up on you. It's going to push upward against you, so that must mean that you were pushing against the chair. Okay? Equal in magnitude but opposite in direction. And then lastly, number 10, which of Newton's laws best describes why motorists should wear seatbelts? Is it going to be the first law, second law, third law, law of gravitation? Which one is it? Well, E is not an option. D is not an option because we never talked about the law of gravitation. So let's think about this. This is the law of inertia. We could sum it up to that. This is the law of inertia. This is F is equal to M times A. This is the cause and effect. Third law is cause and effect. Every reaction, what could I say? Every reaction, or every action, sorry, every action has an equal and opposite reaction. Okay. So we're talking about why motorists should wear seatbelts. Do we want to talk about every action has an equal and opposite reaction? You could. You definitely could. Like if you were to talk about what would happen during a car crash and you talk about like you suffering injuries from wearing a seatbelt, like rug burn, maybe a broken nose from the airbag, or maybe you break an arm. Something that's very common is that people break their collarbones in an accident because, and just so you know, collarbones are actually made to be broken. That's why they're there. So basically your shoulder blade doesn't stab you. Collarbones break. So there you could talk about, well, after or during a crash, you're going to have injuries. And we know that because, well, there's an opposite reaction to every action force. You push on the seatbelt, well, that seatbelt is going to push right back on you, right? Whatever amount of force you push on that seatbelt or that airbag, it's going to push right back onto you. But is that really an explanation as to why we should wear seatbelts? Not really. That's an explanation as to what happens when we wear seatbelts. Is that we, instead of dying, we just have some minor injuries. We have some cuts and bruises. So it's not going to be the third law. Is it going to be the second law? Again, another way is that you could say that this is the second law is describing what's happening. Well, because you have this amount of mass, because you are accelerating this at this rate, you're going to have this amount of force being applied to you. Is that really a reason why? Or could you really have an explanation as to why you should wear seatbelts using this? You could. But I'm going to say no to that one because that just tells you how much force was applied during a car accident. So really, it's going to be A. So why is it A? Well, it's because of this. Which one explains why motorists should wear seatbelts? Why should you wear seatbelts? Well, if you're moving at 60 miles an hour, the car that you're in is moving at 60 miles an hour. That means you in the car are also moving 60 miles an hour. If a car hits a wall or a guardrail or another car and it comes to a stop in less than a second, the car will be at 0 meters per second. The car will be at 0 miles per hour. But you, the passenger, the driver, are going to continue to move at 60 miles an hour, roughly speaking. So in order for you to more or less become part of the car, so that when the car is hit, and goes to 0 miles an hour in 2 seconds, you will also go from, say, 60 miles an hour to 0 miles an hour and stay in place, stay in the same spot within, say, 2 seconds. Okay. So arguably the first law is what we would use in order to argue as to why someone should wear seatbelts. It's because when the car stops, you're going to keep on moving whatever rate the car is moving at. You're going to fly through the windshield. You're going to fly past whatever is behind you, or sorry, in front of you. Okay, you're going to slam into a car seat. You're going to slam into someone else who's in the car. And in order to prevent that from happening, we have to more or less overcome this law of inertia and more or less game it to our advantage. Lock ourselves in to be part of the car with seatbelts. Put in airbags so we don't bust our face and don't bust our arms and our legs as much as we otherwise would if they weren't there. Okay? So definitely a law of inertia. All right, and that is just the check your understandings for Unit 5.2 notes. So if you still have any questions for me, guys, make sure you reach out. I'll see you in the next one.